video. Okay, so here we are talking about the signal S6, right? We are talking about the signal S6. So S6 intention is which is used for indicating whether the system is having the control over the system bus or not. Okay, now. So in the last class we gone with one diagram. So I think yeah, gone with one diagram. So sometimes, most of the cases, the microprocessor is the one which is having the control over the system bus. But here are somewhere when you are supposed to exchange a bulk amount of data between the devices. At that time, we are not allowing the microprocessor to perform that kind of data transfer operation because of there is a restriction of the data bus. Means a bulk amount of when we are allowing the microprocessor to exchange a bulk amount of data, then it is going to take more time to exchange the data, to transfer the data or to receive the data. So to overcome that one, we are having one technique called as a DMA technique. DMA technique is nothing but the direct memory access technique. So that technique is the one which is going to be exchange bulk amount of data in the megabytes format instead of in the 16-bit format. It is going to be exchange the data between the devices in the megabytes format. In the last class we took the what is that, some diagram like this, right? Okay, let me take the same thing. So I'm going to take over here, which is yeah. So I'm assuming this is a MP. This is a RAM, and this body is a DMA, and this one is a hard disk, which is actually H/D hard disk. If you want, you can take it as a pen drive, right? Pen. Okay. Now, when you are allowing the microprocessor, let us suppose I would like to exchange the data between the hard disk and pen drive. It is going to be done via the RAM space. It is going to be done via the RAM space. Even though it is a pen drive is a secondary storage device, the hard disk is also the secondary storage device. But when you would like to exchange the data, actually the exchanging of data is going to be done via the RAM. It is not going to be done directly from the hard disk to the pen drive, because for every pen drive we are supposed to have one driver that is there in the RAM space, and the RAM space is allocated for each and every device. Whenever you are connecting the external devices, then obviously RAM space is allocated for each and every device. For each and every device, there is a RAM space allocated inside the memory. So that's why the information is going to be exchanged from the hard disk into the hard disk to the pen drive via the RAM. Hard disk to the pen drive via the RAM. So when you are trying to perform a bulk amount of data, as I said in the last class, that 500 MB data, let us suppose I would like to exchange the 500 MB data, then if you are asking the microprocessor to perform that kind of operation, then obviously the microprocessor is going to be takes more time, because the microprocessor, whatever the 8086 microprocessor we are having, it is able to send the information in the 16-bit format. So means 500 MB data is divided into the 16-bit format. So if you are sending the information in the 16-bit format, that is nothing but the word format. In order to exchange the in order to transfer the 500 MB data in the 16-bit format, it is going to take more time. It is going to take more time. Instead of that, whenever a bulk amount of data need to be exchanged, then we have one technique called as a DMA technique. DMA technique is nothing but the direct memory access technique. Direct memory access technique. So when the direct memory access technique, DMA technique, would like to involve in exchanging the data, bulk amount of data from the hard disk into the pen drive, from the hard disk into the pen drive via the RAM, at that time this DMA is going to be generates one request signal to the microprocessor. It is going to be generates one request signal to the microprocessor. So this request signal is called as a hold signal. We are going to study about this one also. So just remember, it is a hold signal. It is going to be generates one signal called as a hold signal to the microprocessor. If at all the microprocessor is not doing any kind of important work, if at all the microprocessor is not doing any important work, it is not doing any important work, then immediately what it will do means it will generate one more signal called as a hold acknowledgement signal, HLDA, hold acknowledgement signal to the DMA technique, indicate to the DMA controller. So in order to implement the DMA technique, we are having one controller called as a DMA controller. So the microprocessor is going to be transfers one acknowledgement signal to the DMA, one acknowledgement signal to the DMA, saying that I am ready to relieve the control over the bus. Actually, that whenever the DMA wants to exchange a bulk amount of data, at that time it will ask the microprocessor with the help of the hold signal that I would like to take the it will generate one request signal to the microprocessor in terms of the hold. Okay, now so hold signal means indirectly it is asking, indirectly DMA is asking the microprocessor to relieve the control over the system bus, and in other way indirectly DMA is saying to the microprocessor that I would like to take the control over the system bus. If at all the microprocessor is not doing any kind of important work, then immediately it will send the acknowledgement signal to the DMA controller saying that yeah, you can take the control over the system bus. You can take the control over the system bus. Once the DMA controller, whatever the DMA technique means exchanging a bulk amount of data, means DMA is nothing but the direct memory access, means exchanging the data between the peripherals and the memory without involvement of the microprocessor. So that is called as a DMA technique. In order to perform that DMA technique, we are having one controller called as a DMA controller. Now, once the DMA controller receives the acknowledgement signal from the microprocessor, then immediately this DMA technique, DMA controller is going to be gains the control over the system bus. It is going to be gains the control over the system bus, means the address bus and the data bus now under control of the DMA controller, under the control of DMA controller. So in order to show whether the system bus is under the control of microprocessor or the DMA, we are having S6 signal. We are having S6 signal. So S6 signal indicating that whether the microprocessor is having the control over the system bus or not. So if at all the S6 status, if you are reading the S6 signal status as a 1, okay, now if you are reading this status as a binary 1, then obviously microprocessor is having the control over the system bus. If you are reading this status as a 0, then some other bus master, some other device, like I'm just taking DMA DMA controller as one example. We have some other bus masters also. So DMA means if I am taking the DMA, then the DMA is having the control over the system bus. Microprocessor is not having the control over the system bus. Means the main intention of the S6 signal is to indicate whether the system bus is under control of microprocessor or some other bus master. So to indicate that one, we are having the S6 signal. Okay, so DMA controller, yeah, let's come back to the DMA technique. So once the acknowledgement received by the DMA controller, what it will do means it is having the control over the system bus now, like address bus and the data bus. This one is going to be generates the address, and this one is going to be gives the data bus. Okay, now using the address and the data bus, it is going to be exchange the data between the hard disk and pen drive via the RAM in terms of the different sizes. It purely depends on the DMA controller capacity. It purely depends on the DMA controller capacity. Some of the controllers are able to exchange the data in the 1 MB format. 1 megabyte is going to be transferred per second. So every time it is going to be transferred the 1 megabyte. Nowadays we are having the 10 megabytes also. Nowadays we are having the 10 megabytes and 16 megabytes. That purely depends on the speed of the devices which we are using, means between which device you would like to exchange the data, that purely depends on the speed of those devices also. Nowadays it is a 16 MB, or if you are taking the USB 3.0 version, it is able to, means you are able to exchange the data in the 20 MB, 30 MB, 40 MB format also. Okay, so means instead of, irrespective of the data size of the microprocessor, if you are allowing the DMA technique, then it is going to be exchange the data in the bulk format. It is in the 1 MB means it is a 20-bit data. Yeah, actually it is in the 20-bit format. Okay, M is nothing but the 2 power 20 format. That much of data is going to be exchanged. But if you are taking the microprocessor, then it is able to send the information in the 16-bit format, not in the megabytes format range. Okay, so this is one of the example to explain. So if you are getting confused with all these things, just remember that S6 signal is used for indicating the status of the system bus, whether the system bus is under the control of microprocessor, whether the system bus is under the control of some other bus masters. One of the example for some other bus masters is a DMA technique. Okay, so that's it. So the next case is, let's go to the S5. So S5 main intention is, it is used for indicating the status of the interrupt flag. We are having the IF flag now. We are having the interrupt flag in the flag register. in that flag register, in order to show the present status, if you would have enabled the interrupt, that interrupt status is going to be indicated by the S5 signal. That signal. Okay. So that interrupt status is going to be indicated by the S5 signal. Next case is we are having the S4 S6. The main intention of the S4 S6 is we means right now in which segment the microprocessor is working, means in order to show or I can say that S4 S3 signals are showing the present working status of the microprocessor, whether it is working in the what is that extra segment, whether it is working in the stack segment, whether it is working in the code segment, whether it is working in the data segment. Means currently the microprocessor is working in which segment, that is going to be indicated by the status signals S4 and S3. S4 and S3. So if you are reading the status signal S4 S3 as a 0 0, then it is the alternate data, means the microprocessor is working in the extra segment. The microprocessor is working in the extra segment. If it is a what is that 0 1 combination, if the S4 S3 combination is a 0 1, then the microprocessor is working in the stack segment. Okay, now if it is in the 1 0 combination, then the microprocessor is working in the code segment. If it is the 1 1 combination, then the microprocessor is working in the data segment. Okay, now so microprocessor is working in the data segments. Don't get confused. This combination for ES, this combination for SS, this combination for CS, this combination for DS. Okay, now so means if you are reading the these two say status signals as a 0 0, then the microprocessor is working the extra segment. 0 1, the microprocessor is working the stack segment. 1 0, the microprocessor is working the code segment. 1 1, the microprocessor is working in the data segment. Like that, these signals are showing their status in order to show where exactly the microprocessor is currently working. So the next case is, next signal is yeah, status pins. Okay, now so we have seen the S3 the total number of status signals which are provided by the 808 microprocessor are 8 status signals. They are from S0 to S7. They are showing from S0 to S7. We have seen the what is the use of the S3, S4, S5, S6, and S7 is always high. Now S7 status signal is always high. So the next case is a we are having the 3 more signals. This one is a S2 bar. Unfortunately, it is not written over here. It is a S2 bar. So it is a S2 bar. Okay, S2 bar, S1 bar, S0 bar. So these three signals are showing the present operation which is going on inside the microprocessor. What kind of operation which is going on inside the microprocessor, means it is showing the present operation status, whether the microprocessor is performing the opcode fetching operation, whether the microprocessor is performing the hold acknowledgement, that is nothing but sorry, whether the microprocessor is performing the read operation, the microprocessor is performing the write operation, whether the microprocessor is not in the it is not working, or it is in the ideal position, means it is not working and it is simply sitting ideally. Okay, now so in order to show the present status of the microprocessor operation, what kind of operation which is going on inside the microprocessor, in order to show that one, these three signals are helpful for us. Means if you want to know the present status of the microprocessor, you simply read these three signal status, then you will come to know that what kind of operation which is going on inside the microprocessor, means what kind of operation it is performing, whether it is performing the memory read, memory write, IO read, IO write, or it is halting the operation, or it is performing the opcode fetching operation, or it is in the ideal mode. In order to show the what kind of operation is going on inside the microprocessor, we are having the three status signals. These two for indicating the in which segment it is working, microprocessor is working currently, and these three for showing the what kind of operation is going on inside the microprocessor at a particular point of time. If you are reading these three signal status, then you will come to know that one. So let's see the combinations of those three signals. Okay, so here we are having the signal. Okay, so if the S2 star, where from here onwards, wherever you are seeing the star symbol, just remember that it is a bar, S2 bar. Actually it is a S2 bar. So S2 bar, S1 bar, and S0 bar. You can avoid the star now. Okay, now you can avoid the star. Star is indicated for is used for indicating the active low signal format. Okay, so if you are reading these three signal status from the microprocessor as a 3 zeros, then the microprocessor is performing the interrupt acknowledgement operation. The microprocessor is performing the interrupt acknowledgement operation. If you are reading these three signal status as a 001, then the microprocessor is performing the read operation with respect to the IO device. 010 combination, it is performing the write operation with respect to the IO device. And 011 combination, then it is not performing any operation, it is in the halt mode. And if you are reading this one as a 100 combination, then it is performing the code access, means opcode fetch operation. Code access means it is performing the opcode fetch operation, opcode fetching operation. Okay, now opcode fetch, I'll write in simple short, it is a opcode fetch operation. Okay, it is performing the opcode fetch operation. If you are having the 101 combination, then microprocessor performing the read operation with respect to the memory. Previously, read operation with respect to the IO device, write operation with respect to the IO device. Now if it is a 101 combination, it is a read operation with respect to the memory device. What 110 combination, write operation with respect to the IO device. And 111 is nothing but it is in the ideal mode. It is not doing any kind of operation. It is not doing any kind of operation. Okay, so here the code access is nothing but opcode fetching operation, opcode fetching operation. So if these are the three status signals which are used for indicating the what kind of operation which is going on inside the microprocessor presently. Present operation which is going inside the microprocessor. In order to show that one, that means we are having the three. By reading these three signal status, we will come to know what kind of operation which is going on inside the microprocessor. Okay, so the next case is, yeah, we have seen this one. So the next is a, yeah, as I said, S4 S3, they are indicating whether the microprocessor is working in the extra segment, stack segment, code segment, or the data segment. And we have seen the S5 S6 also. So the next case is the interrupt concept. Okay, the next case is the interrupt concept. So what is the interrupt actually? We have defined the interrupt, right? What is the interrupt? Okay, I hope you remember the interrupt concept. So what exactly the interrupt? Okay, interrupt, what exactly the interrupt? What exactly the interrupt? Okay, so interrupt is nothing but it is a request coming from the external or internal resources. It is a request coming from the external or internal resources. It is a request coming from the external or internal resources. Okay, so what is the external resource and what is the internal resource is a question. Okay, so external resources means if the request is coming from the IO devices to the microprocessor, then it is called as a external resource. If the interrupt is coming from the means if the interrupt is generated using one of the software instruction, then it is called as a internal request. Okay, internal request coming from the internal resource. It is a request coming from the internal resource. What exactly the interrupt is nothing but it is a request actually. Okay, now so some of the textbooks or some of the people used to explain that interrupt is nothing but it is a disturbance. Actually, it is not the disturbance. In the formal, it is kind of disturbance only, but in the formal way, it is a request actually. It is a request. So we don't have the disturbance without any reason, right? We don't have the disturbance without any reason. So obviously there is a work need to be done for that particular disturbance. So I'm not taking the word disturbance, I'm taking the word it is a request. Interrupt is nothing but it is a request coming from the external or internal resource. Please remember this point because we may have the short question in the semester exams. Okay, now interrupt is nothing but it is a request coming from the internal or external resources. Now, so when you are taking the I'm not sorry. I'm sorry, no. Okay, so let us define the in just note it down. I'm not going to define the definition. Uh, just note it down. Interrupt. Okay, so interrupt means it is a request coming from the internal or external resources. There are two types of interrupts actually. Depending on the resource, there are two types of resource interrupts. One is a hardware interrupt, and another one is a software interrupt. Okay, another one is a software interrupt. One is a hardware, another one is a software interrupt. Software interrupt. One is a hardware interrupt, another one is a software interrupt. Hardware interrupt means if the request is coming from the external resources, that is the IO devices or any peripheral is generating one request to the microprocessor to get the function, to get the attention of the microprocessor, then it is called as hardware interrupt. If we are using one of the instruction, so in the instruction set we have seen one thing called as a INT space, the syntax I am writing. So INT space type. INT space type is nothing but it is a INT is nothing but it is an interrupt instruction. So we are having the 256 types of interrupts, 256 types of software interrupts. So for every interrupt we are having the prelocated uh, pre-allocated memory space. So I'm not coming to that point. Just remember that we are having the hardware interrupt and software interrupt. In the software interrupt, if you want to know one of the example for the software interrupt, it is the INT type. So we have seen some what is that examples, right? So means in the program we have taken we used to terminate the program with the INT03H. Okay, now INT we used to terminate the program with INT03H. INT03H is nothing but it is a software interrupt. 03H is indicating that 03H is having the operation of breaking the execution. It is having the operation of breaking the execution. Okay, now, so that is the INT03 type interrupt. Okay, so it is a software interrupt. Now under the hardware interrupt, there are again hardware interrupt is further classified into two types. One is a mandatory interrupt, another one is a non-mandatory interrupt. One is a mandatory interrupt, another one is a non-mandatory interrupt. Mandatory interrupts are called as a non-maskable interrupts. Mandatory interrupts are called as a non-maskable interrupt. Non-mandatory interrupts are called as a maskable interrupts. One is a non-maskable interrupt. Mandatory interrupts are nothing but the non-maskable interrupts. Another one is a maskable interrupt. Let me tell you a simple example. So let us suppose we are in the physical, we are physically existed in the classroom, and I am giving the lecture. If there is a request coming from the student at the doorstep, if the request is coming from the student at the doorstep, let us suppose I am doing the very important work inside the classroom, means I am giving the serious lecture for the student, and obviously there is a request coming, means one of the late student is there at the doorstep and there is a request coming from that student. I may or may not immediately respond to that particular request. I may or may not immediately respond to that particular request. Okay, now, so that particular request which is coming from the student. Okay, so that kind of interrupt is called as a maskable interrupt. Maskable means I can oppose the request. So I'll come to that means I'll accept the student request, but not immediately. After explaining the serious explanation in the classroom, after done that one, I'm going to ask the student to come into the classroom. Okay, now I'll give the permission. Let us suppose during the lecture there is a request coming from the doorstep by the principal. Okay, now principal is generating one request, or the request may be coming from the carried by the IR some other one, or sometimes we may have the principal at the doorstep itself, classroom doorstep. Then immediately what I'm supposed to do? I can't oppose the principal, right? So I have to accept the principal request immediately. Principal request immediately. Otherwise, I would have been out of the college. Okay. So means I need to attend that request immediately. So that kind of request is called as a non-maskable interrupt. That kind of interests are called as a non-maskable interrupt. Or in simple short, we can say that mandatory and non-mandatory. Mandatory means request coming from the principal. Non-mandatory means request coming from the students at the doorstep. Okay, so here as I said, we are having the hardware interrupts. Now under the hardware interrupts we are having the maskable interrupt as well as a non-maskable interrupt. Maskable and non-maskable. Okay, maskable interrupts are nothing but they may or may not executed or attended by the microprocessor immediately. Okay, now they'll attend means microprocessor is attending these requests also, but not immediately. Sometimes it may be immediately, sometimes it may not be immediately. If I'm free in the classroom, then definitely I'm going to allow the student immediately once the request is generated at the doorstep. So if I'm not in the free mode, I'm giving the serious lecture in the classroom, obviously I'm not going to attend that request immediately. Okay, now, but when the principal comes at the doorstep, then definitely I have to attend that particular request immediately, whether you are in the serious explanation or whether you are not giving any lecture in the classroom. Okay, now, irrespective of your present status, irrespective of my present status in the classroom, I have to attend the request coming from the principal immediately. Request coming from the principal immediately. So that is called as a non-maskable interrupt. So here we are having the two types of interrupts now. One is a maskable. I'll allow mask. Don't get confused. Maskable means I'm not going to attend that one. I'm going to attend that one when I'm free. But non-maskable means I should attend that one whether whether I'm free or not, irrespective of my present status. I have to attend that particular request. I have to attend that particular request. Okay, so that kind of request is called as a non-maskable one. So NMI signal, based on this, 8086 microprocessor is providing the two types of interrupts. 8086 microprocessor is providing the two types of interrupts. One is a non-maskable interrupt and another one is a maskable interrupt. Non-maskable interrupt is nothing but NMI pin, and maskable interrupt is nothing but the INTR, interrupt request, INTR pin. Okay, now Sima, for the non-maskable interrupt we don't have any acknowledgement signal. So what exactly the acknowledgement? In the previous days, means just 5 to 10 years back, I think 10 years back, when you are applying for a job or when you are applying for PG entrance or anything, we used to send that one through the post, or we used to directly submit at the head office. But when you are submitting directly at the head office or through the post, we used to have the acknowledgement signal. Acknowledgement means your form is reached to the destination. It doesn't mean that your form is accepted, but it means that your form is reached to the destination where exactly you would like to send. Okay, your form is reached to the destination. So that is the intention of the acknowledgement. So here also, whenever we are having the request, for every request we are having the acknowledgement. For every request we are having the acknowledgement. Okay, but for the maskable interrupt, in that also, for the maskable interrupt only we are having the acknowledgement. For the non-maskable interrupt we don't have the acknowledgement, because we are immediately responding to that particular request. For the non-maskable interrupt or mandatory interrupt, we are immediately responding to that particular interrupt. So that's why we don't have any acknowledgement signal. For the maskable one, we are not responding immediately. Okay, we are not responding immediately. So that's why we should have the acknowledgement. That's why we should send the acknowledgement to that particular signal. Okay, now so means for the NMI we don't have the acknowledgement signal. For the IA, but for the INTR we are having the acknowledgement signal. We'll come to that acknowledgement signal also as we move on. So here NMI is nothing but the non-maskable interrupt. Okay, now whenever we are having the mandatory devices, there are some crucial devices, crucial areas inside the system design. If that part is not working in the proper way, then immediately non-maskable interrupt is going to be generated. For example, you are having your personal computer. So when you are started your system, uh, I'm taking one mandatory condition. When you soon after you started your system, if the fan which is planted on the top of your microprocessor, if the fan is not working properly, which is installed on the top of the microprocessor, then immediately the microprocessor is going to be generates the NMI signal, and your system is going to be abruptly shut it down all of a sudden. Okay, now so because uh, for a fraction of seconds your fan is not working. Let us suppose if for a fraction of seconds which is installed over the microprocessor, the fan which is installed over the microprocessor is not working, then definitely your microprocessor is going to be burst. Your microprocessor is going to be burst. So that's why the fan functionality is connected as a non-maskable interrupt to the microprocessor. The fan functionality is connected as a non-maskable interrupt to the microprocessor. If the fan is not working, within the fraction of seconds the microprocessor will come to know that, and it is shutting down the system all of a sudden. It is shutting down the system all of a sudden. Okay, now so that is one of the area I just focused for the example of non-maskable interrupt. And we are having the INTR now, maskable interrupt. That may be any kind of interrupt. Let us suppose I connected the pen drive. If the microprocessor is doing the important work, then the pen drive is generating one request to the microprocessor saying that I just installed means I just connected to you. So microprocessor may or may not work its functionality immediately depending on its present status. So we are having the maskable and the non-maskable interrupt. Again, I am saying that for the non-maskable interrupt we don't have any acknowledgement. For the maskable interrupt we do have the acknowledgement. So that acknowledgement signal for the INTR we are going to see as we move on in the instruction in the pin diagram. Okay. So the next case is yeah INTR. Uh, the signals in the minimum mode, the signals in the minimum mode. Okay, so we are having the maximum mode signals and we are having the minimum mode signals. Pin number from, oops, there is a mistake. Yeah, it is not a mistake actually. I would like to show some other one. Okay, so here 33 pin. Go back to your pin diagram. I hope you have drawn the pin diagram of 8086 microprocessor. Uh, Go to your pin diagram of 8086 microprocessor. In that we are having the 33 pin. 33 pin is indicating to show whether the microprocessor is working under the minimum mode or in the max mode. To show whether the microprocessor is working under the minimum mode or in the max mode. If the microprocessor is working in the minimum mode, then we are supposed to connect the 33 pin to the plus 5 volts. I explained that one in the previous class. We are supposed to connect that one to the plus 5 volts because the minimum mode functionality is a active high signal. Maximum mode functionality is a active low signal. So minimum mode functionality is a active high signal. Maximum mode functionality is a active low signal because we have the bar over the max mode signal name and we don't have any bar over the minimum mode signal name. So as I'm configuring the 8086 microprocessor under the minimum mode, I'm connecting the plus 5 volts to the 33 pin. Plus 5 volts is nothing but the VCC. I'm connecting the VCC to the I'm connecting the VCC to the I'm connecting the VCC to the 33 pin. So when I'm connecting the VCC to the 33 pin, we are indicating that the microprocessor is configured under the minimum mode. Okay, now let us go for the explanation of the minimum mode signals. So hold means we have seen just a few minutes back in the same video. We have seen exactly the DMA technique. We have seen one technique called as a DMA, direct memory access. So it is generating means DMA controller. For implementing the DMA technique is nothing but exchanging a bulk amount of data between the peripherals and memory without involvement of the microprocessor is called as a DMA technique. DMA technique is nothing but exchanging a bulk amount of data between the devices and the memory, between the peripherals and the memory without involving the microprocessor, without involvement of the microprocessor is called as a DMA technique. In order to implement this DMA technique, we are having one controller called as a DMA controller, direct memory access controller. So that DMA controller is generating the hold signal to the microprocessor. That DMA controller is generating the hold signal to the microprocessor using the pin 31. So as I said, the hold signal to the microprocessor means it is a kind of maskable interrupt. It is not the non-maskable interrupt. Okay, now. So it is a kind of maskable interrupt. It is a kind of maskable interrupt, not the non-maskable interrupt. It is a kind of maskable interrupt. Means if the microprocessor is doing some important work, so when it is doing some important work, obviously it need to have the control over the system bus. It need to have the control over the system bus. Means whenever the microprocessor is not interested to relieve the control over the system bus, at that time it is not generating the acknowledgement signal to the microprocessor to the DMA controller. Actually request is coming from the DMA controller to the microprocessor. So if I'm taking the DMA controller over here, request is coming from the DMA controller to the microprocessor. Request is coming from the DMA controller to the microprocessor using the hold signal. Using the hold signal, DMA controller generating the hold request signal to the microprocessor with the help of the hold, saying that I would like to take the control over the system bus. If the microprocessor is not ready to relieve the control over the system bus, then it is not generating the acknowledgement signal to the DMA. If the microprocessor is ready to relieve the control over the system bus, then it will generate the acknowledgement signal to the DMA saying that I am relieving the control over the system bus. Or other way of explanation is you can take the control over the system bus. You can take the control over the system bus. So means hold is a maskable interrupt. Remember that hold is a maskable interrupt. It is not the non-maskable interrupt. So for this particular hold signal, we are having the acknowledgement signal, which is nothing but the HLDA. Means whenever the DMA controller receiving the acknowledgement signal, then only it will come to know that I'm having the control over the system bus. If it is not receiving the acknowledgement signal, then it realizes that microprocessor is not ready to relieve the control over the system bus. Okay. So the next case is the WR pin. WR pin is nothing but write operation. Remember, whenever you are means let us suppose the DMA controller is having the control over the system bus. Means it is generated the hold signal to the microprocessor, and microprocessor is generated the acknowledgement signal to the DMA. So now the controller over the system bus is uh, means who is having the control over the system bus? The DMA controller is having the control over the system bus. Okay. So when the DMA is having the control over the system bus, at that time we have seen some pins. Okay, like RD bar, and we are going to see one more pin, which is the WR bar. There are some other pins also there. As we move on, we will see all those things. We are having one more pin called as the WR bar. Okay, WR bar. These pins are going to be tri-stated during the DMA technique operation. These pins are going to be tri-stated. Tri-state means tri-state or the high impedance state. Tri-state means which physically there is a connection between the peripheral. Let us suppose I'm having the memory device right over here. I'm having the memory device. It is a memory device. Okay, now. So I'm having the memory device. Obviously, we are going to have the write signal. We are going to have the write signal to the memory device now. So this write signal is connected to the memory now. So it is physically existed. Connection is physically existed. But when the microprocessor is having the releasing the control over the system bus to the DMA controller, or the DMA controller is having the control over the system bus, at that time this signal is going to be there in the tri-state mode or in the high impedance mode. Tri-state mode means physically connection is existed, but virtually it is disconnected. The RD signal is also virtually disconnected. WR signal is also virtually disconnected. Whenever the DMA controller is having the control over the system bus, at that time read signal, write signal are in the tri-state mode. Means they are in the virtually disconnected mode. So that is about the DMA controller. And the write signal is nothing but to perform the write operation by the microprocessor on the memory device or in the IO device. We are going with the WR bar. Next one is the M/IO. So M/IO means we are having the read signal as well as the write signal. We are having the read signal as well as the write signal. In order to differentiate whether that read operation or the write operation, this read signal or the write signal, whatever the write signal which we have seen in the last class. So whether this particular read signal or write signal, generated to the memory or IO device, that is going to be differentiated by this particular M/IO pin. That is going to be differentiated by the M/IO bar pin. If at all this particular M/IO bar pin status is M/IO bar. So M/IO bar status is equals to the what? 1. If the if this particular pin status is a 1, then microprocessor is performing the read operation or the write operation with respect to the memory, because memory is the active high signal. IO is the active low signal. Means if you are reading the M/IO bar status as a 1, then the microprocessor is performing the read write operation with respect to the memory. So if you are reading this status as a 0, it is equals to the 0, then the microprocessor is performing the read write operations. These read and write signals are related to the IO device. Means for the IO device as well as the memory device, we have the common read signal as well as the write signal. But in order to differentiate whether that particular read signal or write signal generated to the memory device or the IO device, that is going to be done with the help of the M/IO bar pin. If the M/IO bar pin status is equals to the 1, then we are performing the means these read write signals are generated to the memory device. And if this particular M/IO bar pin status is equals to the 0, then these read write signals are generated to the IO device. Okay, now. So That is about the that is the intention of the n slash IO bar to differentiate whether the read write signals are related to the memory or the IO devices. We are having the n slash IO bar, and another one is the dt slash r bar. Dt slash r bar is nothing but the data transmit and the receive signal. Data transmit and the receive signal. This dt slash r bar is used for indicating the data direction, whether the data is transmitted from the microprocessor to the peripheral device or the memory device, whether the data is going to be received from the peripheral device or the memory device into the microprocessor. So dt slash r bar is used for indicating that one. Means the dt slash r bar is indicating the data direction on the data bus. It is indicating the data direction on the data bus, whether it is from the microprocessor to the memory device or the IO device, from the IO device or memory device into the microprocessor. So in order to indicate the direction of the data which is flowing on the data bus, we are having the dt slash r bar. We are having the dt slash r bar. And another case is a DEN bar, data enable signal. Data enable signal. This data enable signal main intention is to enable the data bus buffers, external data bus buffer. To enable the external data bus buffer, we are using the DEN bar. So what exactly the data bus buffer will define during the system components. Just remember that this one is used for enabling the data bus buffers. This signal is used for enabling the data bus buffer. What exactly the data bus buffer, we'll see as we move on. Okay now. So the next case is a ALE. ALE is nothing but the address latch enable signal. ALE is nothing but the address latch enable signal. Okay now. So what is the intention of the ALE? To demultiplex the multiplex lines. We are having the multiplexed address lines now. Address lines and the data lines and the address lines and the status lines now. To demultiplex them, we are having the ALE signal. ALE is nothing but the address latch enable signal. If the ALE status, ALE signal is equal to the 1, at that time the multiplex lines are acting as the address lines. If the ALE equals to 0, then the multiplex lines are acting as the address lines as well as the data lines. Address lines as well as the data lines. And the last one, this one is the last one. Last one is nothing but interrupt acknowledgement signal. We have seen one signal called as a INTR. Na? We have seen one signal called as a INTR. INTR. Na? So this is the interrupt request signal. Na? For this particular interrupt, the acknowledgement signal generated by the microprocessor is the INTA bar. Means INTA bar is a INTR signal is the interrupt signal as an input signal to the microprocessor, and if at all the microprocessor is ready to accept that request, then it will send the acknowledgement signal to the device which is generating the interrupt to the microprocessor using the INTR pin. Okay now, so INTA bar is nothing but it is the acknowledgement signal for the INTR signal. Okay now, so this is all about the minimum mode signal. We will continue with the max mode and the rest of the signals in the next video.